Hello friends, welcome to my channel. Today we are going to study solar PV.
What is cell, module, and array. We'll see the array design. We'll see some factors influencing the electrical design of solar array, such as sun intensity, sun angle, shadow effect, temperature effect, climate effect, load matching, then sun tracking. We'll see peak power point operation, which is also called as MPPT, maximum power point tracking. We'll see the electrical characteristics of silicon PV cell and modules, PV system components, then efficiency, MPPT solar system, PV system designing, and PV powered water pumping. So one by one, we'll go in detail with. So initially, we'll start with the concept of solar photovoltaic. So it is similar to your PN junction diode you are familiar with. So you can see here the construction. The blue color is the N type of layer. Below that there is a depletion layer, and below that there is a P type of layer. So this is a PN junction diode, and finally at bottom there is a back electrical contact. So there are two contacts. One is at the top, this one, and the other one is at the back. And in between that there is N type of semiconductor, P type of semiconductor, and a depletion layer. Okay, and it is sensitive to the light effect. So whenever light falls on a PN junction, and which is sufficient to break the depletion layer, then free electrons can move from one layer to the other layer and current starts flowing. Okay, so you can see here we are connecting it to the external load, say. So whenever the sufficient amount of sun radiations or photons here are called falling on the junction, that time it will start conducting and current will start flowing through it. So it is similar to the photodiode. So in the same way as PN junction diode operates, in the similar way solar photovoltaic operates. So when light falls on the PN junction and it becomes forward bias, then light is converted into electricity. So this was the basic construction. Now going to the specific material and its construction, how it is manufactured. You might have seen this solar array at the rooftop system. So say this outer one is the frame just to hold the solar PV cells or arrays or modules. Inside that there is a glass cover which is at the top. It is to allow the solar radiation to fall on the solar sensitive material. After that, there is a polymer sheet. You can see polymer sheet is there at both the sides of a solar cell, at the bottom side as well as at the top side. So polymer sheet act as a anti-reflecting cover. So anti-reflecting cover because glass cover allows the solar radiations to come inside, and polymer sheet is provided to avoid the anti-reflection. I mean, it will not go back again to the atmosphere, but the light entered through the glass cover will get absorbed through the solar cells. It becomes forward bias and it will carry the load which we have connected on it. So we can convert the light electricity or solar radiations into equivalent electrical energy, and then we can utilize it for our further use. Okay, so this is the construction. So there are main parts are outer frame for holding the solar cell, then glass cover to allow the entry of the solar radiations, anti-reflecting polymer sheets. Then there is a N layer. So we'll go in detail what we have studied in the last slide. So there will be N layer, then PN junction, P layer, and then the terminal. So there are two terminals carried at the backside itself. One is taken from the P layer, the other one is from N layer, and those two terminals are acting as the terminal for connection of the electrical load. Okay, now we'll see the basic operating principle of a solar cell. So as we have studied, this is a solar panel, this is a sunlight falling on it. Now here the cut section I have shown to show you the N layer, P layer, and in between that there is a depletion layer. Okay, so when sufficient light is there and junction becomes forward bias, then flow of electron will take place for the current flow. Okay, so P layer contains majority charge carriers as positively charged holes. N layer contains majority charge carriers as negatively charged electrons. And whenever it becomes forward bias, then electrons can jump from one layer to the another layer crossing the depletion layer. Okay, this you already have studied in physics or in 10th also, I think. So it is just a revision, and current can flow and you can get the electricity. Thus solar energy is converted into electrical energy. So similar diagram I have shown here, which is more clear. Okay, so you can see the junction layers, sun radiations falling on it. Again cut section zoom करके दिखाया है इधर for understanding, and current flow. Now we'll discuss the concept of solar cell, solar module, and solar panel and solar array. So as the hierarchy is shown here, it works in the similar way. I mean, initially we have a PV cell which is small in size, okay, and it has a defined, predefined current and voltage values. Depending upon the power requirement, we can have a module wherein we are using n number of series cells and combination in parallel. So in the given module which I have shown here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 modules are connected in series, and likewise 1, 2, 3, 4, 5, 6. 6 parallel paths are there. Okay. So total 84 PV cells we have used. 12 are in series and likewise 9 are in parallel. Okay. So first series connections are made to increase the voltage level. Suppose each is of 2 volt, then it will be 24 volt, right? 12 cells are there. They are connected in series, so it will be additive. So 12 twos are 24. So one series will give us 24 volt, and let us say it is giving us say 1 milliampere, then 1, 2, 3, 4, 5, 6. So it will give us 6 milliampere. So it is 24 volt, 6 milliampere. I am just taking an example. When we'll actually design the system, you will come to know the specifications of a module, array, cell, everything in detail. Now, I hope you have understood the concept of module. Now, similarly, if we connect number of modules in series or parallel, then we can get a panel. So here we have connected 3 modules in series. So we can increase the voltage level or the current level depending upon our requirement. If we want to increase the current, we have to connect it in parallel, the basic concept. And if you want to increase the voltage, we have to connect it in a series. And at last, there is an array which contains the number of panels connected in series and parallel. Again, for the required power requirements, we are connecting solar panels in series or parallel. Therefore, whenever we design a rooftop system, that time you can see there are n number of solar panels connected in series and parallel depending upon the power generation. Or actually, we decide the number of modules or number of panels depending upon the available area within which we can have a solar farm. And depending upon that, our generation capacity is decided depending upon how many panels we are able to connect in series or parallel. Okay, so it is very simple. We are going to take one of the experiment based on series and parallel combination of solar cell to improve the voltage and current requirements. Now we'll see the mounting of these solar PV modules. So we can mount it in various fashions. The first one is a ground mounted, like I have shown here. So here the roof itself is tilted, so there is no need of a tilt angle, and you can directly put it on a so it is called as a ground mounted, where you are not giving any angle, no any tilt is given to the panel, and directly it is mounted on the top. Okay. Second one is a pole mounted. So pole mounted means this is acting as a pole on which the solar panel is mounted. Now again, if you provide any gearing mechanism, then we can rotate it from east to west to get the maximum efficiency with a single axis tracking. But otherwise, you can fix it at a specific tilt angle wherein we get the maximum amount of solar radiations, and you will get throughout the day the solar radiations, and you will get better efficiency as compared to that of a fixed one. So this is fixed one only, but not flat, but it is tilted at a angle, and that angle is adjusted with the help of a pole arrangement. So it is a pole mounted. Now the third one is a track rack arrangement. So generally track rack arrangement have a gearing mechanism through which we can move the move the rack from east to west. Okay, so here there are some arrangements wherein we can place the solar modules, and this is called as the track rack arrangement. Now, the last type of mounting is the side of a pole. So, poles are there. So, at the side of a pole, some fixing assembly is available in the market. With the help of that, we can utilize the space and we can get maximum amount of solar radiations falling on it. So, if you have a keen observation at our college premises, then you can see this side pole arrangement. Okay, side pole arrangement wherein we have placed these solar panels for operating the corridor lighting. Okay, for that purpose we have used this side mounted solar panels at our Modern College of Engineering. Now we'll see the VI characteristics. Generally, for every device, we call it as a VI characteristics. But understand, for solar cell or PV cell, we always call it as a IV characteristics because we are interested in current as well as in the voltage. Because we cannot operate it with a zero current, we cannot operate it with a zero voltage, but we want sufficient amount of current and voltage to drive a particular load. Okay, so I'll explain you these characteristics first, which I have hand drawn characteristics. So y-axis is a current, x-axis is a voltage. Okay, so we have drawn the characteristics for two different conditions. You can see this is 0 point. So on the left hand side of the zero, it is dark. So characteristics when there is no sun during dark during night period, and right hand side of zero represents the characteristics when it is illuminated. So whenever there is a sun. Okay. Now observe this point which is of the most important, which is of our interest, which is marked by ISC, which is a short circuit current. So at short circuit current, you can see the voltage value is 0. So when the output terminal of a solar panel are shorted together, so whenever it is a short means we are making the voltage 0. So at that time you will get maximum amount of current, that is called as the short circuit current. So this is the current which you will get by shorting the two terminals of a solar panel and measuring the current. That is called as a short circuit current. Now, one more important point is VOC, which is a open circuit voltage. Open circuit voltage means we are not driving any load, so we will get maximum amount of voltage. So up till now you have studied as load increases, voltage will drop down. So when there is no load, voltage will be maximum. That is called as the VOC, open circuit voltage. Means the output terminal of a solar panel are open and solar radiations are falling on it, and you are measuring the voltage, that is called as the VOC, open circuit voltage. Okay. Now the shaded part I have shown with respect to the knee point. Okay, it is called as a knee point, which is called as a operating point, wherein we get maximum voltage and maximum current. If you observe, we are not going beyond this current. Okay, if you observe voltage, we are getting some better voltage at this point, but here current starts drooping. Okay, the voltage is constant, but current is drooping. So this is called as the constant, say constant voltage characteristics at the right hand side shaded part, whereas the left hand side shaded part you can see the current is constant and voltage is varying, but it is not I mean you can consider this part from here to here wherein you get almost constant voltage. So you have to decide what is your operating voltage required for the load, and at that corresponding value what is the maximum amount of current that you can extract from the solar cell, and that is going to be your operating point. And generally the operating point is denoted by the knee point, KNEE, knee point. So this is a knee point where you get the optimistic values of the voltage and current, and we can extract the maximum amount of voltage and current. Wherein you can see at the dark portion, the current is almost zero here. The current is almost zero. After a certain point, I mean, you think of a PN junction diode, which is supplied with a reverse, or which is applied with a reverse current, then it goes into negative region. So in the same way it also goes in the negative region. So up to certain point it can hold its values wherein it will give you zero current, but after that it the whole assembly becomes reverse biased, and the junction will broken. I mean, the device will be no longer in use then after this point. The total breakdown will take place. Okay. So similar characteristics I have shown here along with the power. Now you can see this. This red line shows the IV characteristics, wherein this is the short circuit current which we have studied here. This is VOC, open circuit voltage. See, this is the knee operating point where you get maximum amount of voltage, maximum amount of current, and corresponding power I have shown with a blue line, which is a product of voltage and current. So it will go on increasing to a certain point, and after that it will drop down. Okay. So this is the maximum power point which we are interested to achieve, and this is what we are interested in, and hence this is called as the knee operating point. So ideally we want to operate our solar panel at these values of voltage and current to get the maximum efficiency. Okay. So here we have completed the IV characteristics. Now let us see with the series parallel combinations which we have studied earlier how it will operate. So single crystal we are getting this characteristics. Okay, just now we have seen. So this is the characteristics with a single say solar array. If you connect number of arrays in parallel, you are increasing the current. So on y-axis it is a current. So if you connect the number of modules in parallel, definitely you are going to improvise the current characteristics, but voltage will remain constant. Whereas if you connect number of solar panels in series, so you are moving in voltage line now, because we are improvising the voltage. As they are connected in series, voltage will be additive. When they are connected in parallel, current will be additive. So to improvise the current, we will connect them in parallel. To improvise the voltage characteristics, we'll connect them in series. And whenever you want to improve current and voltage both, and you want higher power, in that case, we should go for series and parallel combination of the solar modules. Okay. So as we have seen in the characteristics, this is a these are the regions. This is constant current region and this is a constant voltage region. But in between that, we get the maximum amount of power which we are interested in.
Thank you for watching. See you guys. Bye.